All right, today we're going to talk about valence shell electron pair repulsion, also known as the VSEPR theory, VSEPR. It's literally a way of taking the valence electrons of the atoms, putting them into the electron configuration, and determining or predicting the shape of each compound or molecule. So, for example, we have ammonia, NH3. So if you look here, the way I do it on the sheet of paper is I just write each element by itself first. So like nitrogen. Nitrogen is in group 15 on the periodic table. And so it has 5 valence electrons. 2, 3, 4, 5. And then there are 3 hydrogen. Each one is in group 1, meaning it has 1 valence electron. So then I have to put them around the central atom here. The central atom, of course, being nitrogen, it has more open electrons or free electrons. So nitrogen goes in the middle. It will have 2 electrons that are considered a lone pair, and then it will be bonded to hydrogen on the other 3 electrons. So what you have here then, just like you see on the screen, is the Lewis structure or Lewis dot structure of ammonia. So then what I can do is turn it to the molecular structure with each bond being a line. Now, instead of you seeing the individual electrons, you now see a bond there. So in this case, there are 2 electrons, so that is a single bond, and then there is 1 lone pair. So here, to figure out what type of shape or molecular geometry this compound has, I have 3 bonded pairs, and I have 1 lone pair. 1 lone pair. Okay, so I'm looking for a 3 to 0. So I come over here. This is in the packet I gave you at the beginning of the year, or if you don't have this molecular geometry table, please get one. So I'm coming down. I know that I have number of bonds are 3, and I have 1 lone pair. So this is not it. So the next one down, there is 3 bonded to 1 lone pair. That's a total number of 4 charged clouds, and that is trigonal pyramidal. So I know that ammonia has trigonal pyramidal. If you look at the screen, I've shown that it has 107 degree bond angle. And so that lone pair takes up a lot of space, which pushes the hydrogen farther down. And so you get here what looks like this 3-dimensional model or ball and stick model of ammonia. And so if we're going about, I'm going to move the camera here. So if I look at water, all right, so same thing. We can look at water, we can look at the ammonia, we can look at methane even. Methane has 4 bonded pairs to 0 lone pairs around that carbon. And so that one, if I look at 4 to 0 here on the screen, 4 to 0 would be tetrahedral. Okay. I might want to lower that also, so if you can see that, here we go. So 4 to 0 here is tetrahedral, and it looks like this, just like you see on your screen for methane. Okay, so in this case, we have 2 electron pairs in the valence orbital. That is linear. 3 electron pairs are trigonal planar. 4 electron pairs is tetrahedral. 5 electron is trigonal bipyramidal. Now, you'll have to pay attention to this bottom one, because in geometry, you learn that something that is 6-sided is actually a hexagon. But in this case of molecular geometry, if it has 6 electron pairs, we actually call that octahedral. And so really, the repulsion of the lone pair is greater than the repulsion of the bonded pair, which takes up a lot more room, which if you look here, on my diagram of ammonia, you'll see this lone pair is taking up so much space. I've kind of drawn it here. It takes up a lot of space, and so it's pushing these hydrogen farther down. Okay, that's because those lone pairs take up a lot of room. So if it's linear, I can put it together, my model kit, and it'll look just like that. My trigonal pyramidal will look just like this. That one is my tetrahedral, so that methane. This one is your trigonal bipyramidal here. Kind of got it on the crease. Trigonal bipyramidal, it's got 3 atoms in the middle and 2 on each axis. And then that is your octahedral. It's got 6 total electron pairs, so that is your octahedral. So I'm going to walk you through the steps I do to answer these molecular geometry questions. So the first thing I do is I draw that Lewis dot structure, okay? So for example, say I have calcium chloride, right? CaCl2. Calcium chloride here. I know that the calcium has 2 electrons in its valence shell because it's in group 2. And then chlorine, of course, has 7 because it's in group 17. Okay, so it looks like this so far, but calcium is going to be in the middle, so it's going to come over here. So really what I would have would be Ca. Okay, something like this. But then I know that I've got, in this case, 2 bonded pairs, no lone pairs, so I'm looking at a 2 to 0. So I know this would swivel up. And so what we'd have chlorine to calcium to chlorine. And if I put those extra spare electrons around the chlorine, it would look like this. And if that's the case, if it's a 2 bonded pairs to 0 lone pairs, I come back here, 2 bonded pairs to 0 lone pairs, that would be linear. Okay. So it would look like this, and then it would be linear. And so at that point, you determine the number of unshared pairs. So like I said, 2 to 0, and then establish the orientation of the electron pairs and describe the geometry. So let's do some more examples together, because now we get into this idea of bonds, right? Whether it's a single bond, double bond, triple bond. So I'm going to look at CO2, okay? CO2. So there is 1 carbon. As you know, carbon is in group 14, so it has 4 valence electrons. Each oxygen has 6. And then I got to put that together. So the carbon and the oxygens are going to come together. But if you notice, there's 4 free electrons, okay? And then there's going to be 2 free electrons on the oxygen. So they're actually going to form double bonds. And then there's going to be 2 lone pairs on each oxygen. Now, what I want you to understand is to figure out the number of bonded pairs to lone pairs, we look just right here around the central atom, and each double bond is only going to count as 1. So in this case, I've got a 2 to 0. All right. So each double bond is going to count as 1 because they move together, and there is no extra lone pairs, so this one would be linear. Okay. Double check right here. 2 to 0 would be linear, and the example here is right here, CO2. Okay. The second one I'm going to cover is HCN. So I have my hydrogen, has 1 valence electron because it's in group 1. Carbon has 4 because it's in group 14. And nitrogen has 5 because it is in group 15. Okay, so carbon's yet again still going to be with my, that doesn't make sense, hold on, I drew one too many here on my nitrogen. Let's get rid of this one here. Okay, sorry about that. I might have whiteout. I'm sorry, I do not. Okay, so carbon is actually going to be the central atom because it has more free electrons. And so in this case, this hydrogen is going to attach here. And then if you notice, there's 3 extra lone electrons on the nitrogen. So those are actually going to form bonds. And that's going to be a triple bond here. So what it's going to look like is HC triple bond to the nitrogen. And then that nitrogen has a lone pair off to the side or up top. So that accounts for all 5 of the valence electrons around nitrogen, 4 around carbon, 1 around hydrogen.
Are you good?
Good. So anyway, so there we have the nitrogen. So what we do is we actually count, yet again, we have 1 bond here, and we count this triple bond as 1. And we're only focused right here on the central atom for the shape or molecular geometry. So it is a 2 to 0, right? 2 bonded to 0. So yet again, it is linear. Okay. So now let's do another one. Let's look at let's just do SF6. Okay. So we have here sulfur has 6. 1, 2, 3, 4, 5, 6. Get rid of that one. Okay. Fluorine, of course, each one has 7 because it's in group 7. 1, 2, 3, 4, 5, 6. So you can draw all those. So what's going to happen is each one's going to have 1 extra valence electron here, 1 free electron. Okay, and then it's going to wrap around sulfur. So here around sulfur we have 6 to 0. So 6 to 0. I look on my sheet here. I have to go all the way down. 6 to 0 is my octahedral. So that sulfur hexafluoride right here is that octahedral. Okay, now say we do like a sulfur oxide, something like that. Okay, so here we have sulfur. There are 6, 1, 2, 3, 4, 5, 6. And then oxygen also has 6. And then the other oxygen also has 6. So what we notice is it's going to be a double bond and a double bond. Okay, so what's going to happen is you think or predict, right, that SO2, that is, scribble that out, the SO2 here, you would think would look like this. S double bond O, double bond O. There is 4 extra, 4 extra, 2 extra, right? So what we have, you'd think would be linear, but in fact, we count these as 1, so we have 2 bonded, and we have 1 lone pair here, so to 1. And if I look on the sheet, 2 to 1 is actually bent. So what it does, we would predict, right? So what we would predict is actually it's bent to look like that. And there'd be 2 lone pairs there. So instead of linear, it would be bent. Okay. All right. So CO2, HCN, CH4 tetrahedral, like I talked about, the ammonia, which is the trigonal pyramidal that I talked about. A water molecule is actually bent, okay? And so this is the diagram I'm actually looking at. It's a closer version, right? If there's total bonds or total bonded pairs to 0 lone pairs, it's linear, right? 4 to 0, it's tetrahedral. 3 to 1, 3 bonded to 1 lone pair is trigonal pyramidal, so forth, so on. And this chart is what you need for the homework, because the first table, you're literally going to draw me the Lewis structure in the first column. Second column of the homework, you're telling me bonded pairs to lone pairs. And then the last column is the shape or molecular geometry. So you just list what it is, right? Is it linear? Is it octahedral? Is it trigonal planar? Is it trigonal pyramidal? So forth, so on. If you need more help, please just email me and let me know.